Imagine you are standing on a highway, and suddenly a car passes by you at 300 kilometers per hour. Your heart races, the sound makes you jump, and before you can even turn your head, the car has already disappeared over the horizon. That speed feels insane, right? Now multiply that by more than 2,000 times. 700,000 kilometers per hour. That is how fast the Parker Solar Probe is traveling right now as you watch this video. It is not just the fastest spacecraft humanity has ever built. It is the fastest object we have ever created, period. Nothing made by human hands has ever moved this fast. And here is the thing that really gets me thinking about this at night. This tiny machine, about the size of a small car, is screaming through space at a velocity so extreme that if you could somehow put it on a track around Earth, it would lap the entire planet in less than 4 minutes. 4 minutes to circle the whole world. Let that sink in for a moment. But speed records are cool and all, sure. However, what really matters here is not just that we built something incredibly fast. What matters is why we did it and what this machine is doing right now. Because the Parker Solar Probe is not racing through empty space for bragging rights. It is diving closer to the sun than any spacecraft in history, surviving temperatures that would vaporize almost anything we know, and sending back data that is rewriting our understanding of the star that makes all life on Earth possible. And somehow, against all odds, it is still working perfectly after years of punishment that should have destroyed it 100 times over. So how did we get here? How do you even begin to build something that can touch the sun and live to tell the tale? And what are we learning from this insane journey that makes all the risk and engineering nightmares worthwhile? Let me take you through this story because honestly, every time I read about this mission, I find something new that blows my mind. First, let us talk about what 700,000 kilometers per hour actually means, because our brains are not really wired to understand speeds like this. When astronauts travel to the International Space Station, they are moving at about 28,000 kilometers per hour. That is already fast enough that they orbit Earth every 90 minutes. The Apollo missions that took humans to the moon reached speeds of around 40,000 kilometers per hour. Even the Voyager probes, which have left our solar system and are now traveling through interstellar space, are only cruising at about 60,000 kilometers per hour. The Parker Solar Probe is moving more than 10 times faster than that. At its top speed during its closest approaches to the sun, if you could somehow take this spacecraft and point it at the moon, it would get there in about 30 minutes. 30 minutes to cover the same distance that took the Apollo astronauts 3 days. And here is something that really puts it in perspective for me. At 700,000 kilometers per hour, the probe is moving at roughly 0.064% the speed of light. That might sound small, but remember, the speed of light is the absolute cosmic speed limit, the fastest anything can possibly go in our universe. This little spacecraft we built is already pushing toward 1/1000th of that ultimate barrier. That is genuinely incredible when you think about it. But speed alone does not tell the whole story. The real question is, how do you get something moving that fast in the first place? You cannot just strap on a massive rocket engine and blast off into the sunset. Space does not work that way. The answer lies in one of the most elegant and clever tricks in all of space exploration, something called a gravity assist. Think of it like a cosmic slingshot. When a spacecraft flies close to a planet, it can steal a tiny bit of that planet's orbital momentum and use it to speed up or change direction. The planet is so massive compared to the spacecraft that it does not even notice the exchange. But for the spacecraft, it is like getting a free turbo boost. The Parker Solar Probe has used Venus for this maneuver not once, not twice, but 7 times. Each time it swings past Venus, it gets a gravitational kick that sends it faster and closer to the sun. Think of it like a skateboarder in a half-pipe, using each pass to build up more and more speed. With every Venus flyby, the probe shaves off a bit more of its orbital energy, allowing it to fall deeper into the sun's gravitational well and pick up even more velocity. The first time the probe flew past Venus, it reached speeds that already broke records. But with each subsequent pass, it got faster and faster. The 7th and final Venus flyby happened in November of 2024, and that set up the record-breaking close approach in December of that same year, when the probe reached its current insane top speed. But here is what makes this even more mind-bending. The spacecraft is not using any engines to go this fast. It is just falling toward the sun, pulled by gravity, accelerating the same way a ball accelerates when you drop it, except there is no ground to hit and no air resistance to slow it down. Just pure, continuous acceleration as the sun's immense gravity pulls the probe faster and faster. When the probe is at its farthest point from the sun, it is moving at a relatively sedate 100,000 kilometers per hour or so. But as it falls inward on its elliptical orbit, the sun's gravity accelerates it relentlessly until, at its closest approach, it is absolutely screaming through space at that 700,000 kilometer per hour mark. Now you might be wondering, okay, so it is going really fast. That is impressive engineering and all. Why go to all this trouble? What is so special about getting close to the sun? Great question, and this is where things get really interesting. The sun is not just a big ball of fire in the sky. It is a roiling, seething, incredibly complex dynamo of plasma and magnetic fields that we still do not fully understand. And that is a problem, because the sun directly affects everything in our solar system. Solar storms, massive eruptions of charged particles and magnetic fields, can race out from the sun and slam into Earth. When they do, they can knock out satellites, damage power grids, disrupt GPS and communications, and even pose radiation hazards to astronauts. In 1859, a massive solar storm called the Carrington event hit Earth and was so powerful that telegraph systems caught fire and auroras were visible near the equator. If something like that happened today, with our modern dependence on electronics and satellites, the damage could be catastrophic. We are talking potentially trillions of dollars in damage and months or even years to recover. The thing is, we are not very good at predicting these storms. We can see them after they happen, sure, but predicting them before they occur? That is much harder. And the reason we struggle is because we do not fully understand the fundamental physics of how the sun works. We do not understand why the sun's outer atmosphere, the corona, is millions of degrees hot while the surface below it is only a few thousand degrees. That makes no sense. It is like the air above a campfire being hotter than the fire itself. We also do not fully understand how the solar wind, that constant stream of charged particles flowing out from the sun, gets accelerated to the speeds we observe. These are not just academic questions. Understanding these processes is crucial for predicting space weather and protecting our technology and infrastructure. And here is the problem with studying the sun. You cannot do it from far away. Imagine trying to understand how a waterfall works by standing a kilometer downstream and analyzing the river. You would miss all the crucial action happening right at the waterfall itself. That is what we have been doing with the sun. We have been studying it from Earth and from spacecraft in Earth orbit, which is more than 150 million kilometers away. The Parker Solar Probe is changing that. It is flying directly into the corona, into the birthplace of the solar wind, into the region where all this mysterious physics is actually happening. It is like going to the waterfall and sticking your head right into the spray to see what is really going on. At its closest approach, the Parker Solar Probe gets within about 6 million kilometers of the sun's surface. That might still sound like a lot, but in astronomical terms, it is incredibly close. To put it in perspective, Mercury, the closest planet to the sun, never gets closer than about 46 million kilometers. The probe is getting almost 8 times closer than that. It is literally flying through the sun's outer atmosphere. And this brings us to perhaps the most mind-boggling challenge of the entire mission. How do you build something that can survive that? At the distance the Parker Solar Probe reaches, the sun's radiation is intense beyond anything we normally deal with. The heat shield on the front of the spacecraft faces temperatures of around 1,377 degrees Celsius. That is hot enough to melt most metals. That is hot enough to turn rock into lava. And yet, just a few meters behind that heat shield, the spacecraft instruments are operating at a comfortable room temperature. Think about that for a second. On one side of a shield, temperatures that would destroy almost anything. On the other side, conditions cool enough that you could survive comfortably in a t-shirt. The heat shield is made of a carbon composite foam sandwiched between 2 carbon fiber sheets. It is only about 11.5 centimeters thick. That is it. less than 12 centimeters between hellish inferno and survivable conditions. The shield works not by conducting heat away, because there is nowhere to conduct it to, but by being an incredibly effective insulator and by reflecting most of the sun's energy back into space. The white coating on the shield is specially designed to have extremely high reflectivity. It bounces back as much of the sun's radiation as possible, and what little heat does make it through is blocked by that carbon foam, which is an incredibly poor conductor of heat. But even with that amazing heat shield, the engineering challenges are immense. Everything on the spacecraft has to be designed to survive not just the heat, but the incredible radiation, the thermal stress of repeatedly swinging between scorching close passes and the relative cold of the outer solar system, and the fact that there is no possibility of repair. Once the Parker Solar Probe launched, that was it. Whatever problems come up, the spacecraft has to handle them on its own. And yet, years into the mission, the probe is still functioning beautifully. Every close approach, it dives through the corona, takes measurements, and then swings back out to a safer distance where it can radio all that precious data back to Earth. Then it does it all over again. Again and again, subjecting itself to conditions that would destroy almost anything else we have ever built. So what has it found? What is all this risk and incredible engineering teaching us? The discoveries have been genuinely surprising. The probe has flown through structures in the solar wind that scientists call switchbacks. These are sudden, dramatic reversals in the magnetic field where the field lines fold back on themselves in huge zigzag patterns. Before Parker, we had hints that these things existed, but we did not know how common they were or how important they might be. Parker has shown that they are everywhere in the inner solar system, and they seem to play a crucial role in accelerating the solar wind. Imagine driving down a highway and suddenly the road loops back on itself like a roller coaster. That is kind of what these magnetic switchbacks are like, and particles traveling along these magnetic field lines get whipped around and accelerated to enormous speeds. The probe has also flown directly through coronal mass ejections, those massive eruptions of plasma and magnetic fields that can cause space weather storms when they hit Earth. But instead of observing them from afar, Parker has been inside them, measuring the structure and evolution of these eruptions from the inside out. It is like being inside a hurricane, measuring the wind speeds and pressure changes from within the eye of the storm itself. One of the most fascinating discoveries has been about dust. Near the sun, the environment is so hot that dust grains simply cannot exist. They vaporize. Parker has confirmed that there is a dust-free zone close to the sun, a region that is just too intense for even tiny particles of dust to survive. This has implications for understanding how planetary systems form and evolve, because dust is the building block of planets. Understanding where dust can and cannot exist helps us understand how planets like Earth came to be. The probe has also been measuring the properties of the corona itself, taking direct readings of temperature, density, and the plasma waves that ripple through this superheated atmosphere. Every close pass adds to our understanding, filling in gaps in our knowledge and often raising new questions that we did not even know to ask. But perhaps most importantly, Parker is giving us the data we need to build better models of the sun and space weather. Each measurement, each observation, helps scientists refine their understanding of the physics at work. And better understanding means better predictions. Eventually, the data from Parker Solar Probe should help us create more accurate space weather forecasts, giving us warning before dangerous solar storms hit Earth. That could save billions of dollars in infrastructure damage and potentially save lives. Now here is something I find particularly moving about this mission. The Parker Solar Probe is named after Eugene Parker, a physicist who, back in 1958, predicted the existence of the solar wind. At the time, his ideas were controversial. Many scientists did not believe him, but he turned out to be absolutely right. The solar wind is real, and it is one of the fundamental features of how our sun interacts with the rest of the solar system. Eugene Parker lived to see the spacecraft that bears his name launch in 2018. He was 91 years old, and he attended the launch. He got to see humanity send a machine to test and expand on the theories he developed decades earlier. He passed away in 2022, but his legacy is up there right now, flying closer to the sun than anything ever has, at speeds nothing has ever reached, doing science that he dreamed of. There is something deeply beautiful about that to me. And the mission is not over. Not by a long shot. The Parker Solar Probe will continue making close approaches to the Sun for years to come. Each pass will continue to return data, and scientists will continue to analyze that data, piecing together a more complete picture of our star. The final close approaches, scheduled to continue through 2025, will push the probe even closer and even faster, potentially breaking its own speed records yet again. But beyond the specific science and the record-breaking numbers, there is something larger here that captures my imagination. The Parker Solar Probe represents what humans can do when we push the boundaries of what seems possible. 50 years ago, the idea of sending a spacecraft into the Sun's atmosphere would have seemed like pure fantasy. The materials did not exist. The engineering knowledge was not there. The computational power needed to plan such a mission did not exist. But we kept learning, kept developing new technologies, kept asking questions, and eventually we figured it out. We built a machine that can touch the Sun. And that makes me wonder, what else can we do? What other seemingly impossible challenges might we overcome in the next 50 years? If we can build something that survives temperatures hot enough to melt steel and reaches speeds that boggle the mind, what else might we achieve? Maybe a mission to another star system, not with humans, but with probes that could make the journey in decades rather than millennia. Maybe missions that dive into the atmospheres of Jupiter or Saturn, or land in the subsurface oceans of Europa or Enceladus. Maybe technologies we have not even imagined yet. The Parker Solar Probe is not just about understanding the Sun, although that is incredibly important. It is also about showing us what we are capable of when we combine curiosity, brilliant engineering, and the will to explore. It is a reminder that the universe is knowable, that we can go to the most extreme environments imaginable and bring back knowledge. It is a testament to the fact that the same species that once huddled around campfires, telling stories about the lights in the sky, can now build machines that fly through the atmosphere of a star. So here is my question for you. When you think about missions like the Parker Solar Probe, what excites you most? Is it the engineering challenge of surviving such extreme conditions? Is it the science and what we might learn about the Sun and space weather? Is it the speed records and the sheer audacity of flying something that fast? Or is it something bigger, the idea that we are still exploring, still pushing boundaries, still reaching for things that seem impossible? Drop a comment and let me know what aspect of this mission captures your imagination, because I genuinely want to know what resonates with you. And if you enjoyed diving into this story with me, make sure to let me know, because there are so many more incredible missions and discoveries out there that deserve to be talked about. Thanks for watching and keep looking up.